For years, the tech industry has operated under a single assumption. If you want to build with real artificial intelligence, you have to tether your software to a massive, centralized server farm. That constant connection carries steep recurring costs. Every query rings up an API fee, user data is routed through external corporate networks, and developers have absolutely zero control over the underlying model weights or update schedules. This dependency also exposes systems to severe geopolitical vulnerabilities. When the U.S. Department of Commerce temporarily suspended Anthropic's Claude 5 models in mid-2026, entire product ecosystems went offline overnight. But a rapid structural consolidation in the open-source community during the summer of 2026 created an ecosystem designed to bypass the cloud entirely. Developers are no longer settling for downloading basic open-weight models. They are compiling complete, locally executable AI stacks that eliminate external rent-seeking from the deployment equation. The foundation of this local deployment starts right at the hardware level, the bare silicon of the GPU. To unlock real speed, engineers had to escape heavy proprietary runtimes that bottleneck consumer graphics cards. A dedicated solution arrived with Zynq, a local inference engine written in the Zig programming language. Instead of forcing workloads through AMD's massive ROCm dependency stack, Zynq drops those libraries completely. By bypassing the legacy software bottleneck, Zynq routes processing directly into a native Falcon compute path, communicating closer to the physical hardware. This direct pipeline pushes prefill and decode speeds past standard servers, hitting a 151% throughput increase on consumer graphics cards. By utilizing these low-level inference engines, developers can treat standard off-the-shelf workstation hardware as independent, high-performance deployment nodes. With the execution path cleared, the next engineering hurdle is memory. Data center neural networks require hundreds of gigabytes of video RAM, raising an obvious question: how do you fit that massive scale of intelligence onto a local machine without crashing the system? The answer relies on aggressive architectural pruning. Engineers take a massive model, like the 120 billion parameter Nematron 3 Super, running it through the Iterative Puzzle framework, a system that systematically slices away redundant parameters to create the highly compressed Nematron Labs 3 Puzzle 75B. Through heterogeneous channel pruning, redundant intermediate nodes are unevenly stripped away, preserving dense clusters only where strictly required for complex logic. Data tokens now travel a streamlined path, drastically shrinking the active memory footprint while keeping core reasoning capacity fully intact. These sophisticated compression algorithms take the bloated processing requirements of the cloud and carve them down into lean, highly efficient computation that runs locally. The final argument for remaining on proprietary cloud architecture has always been precision. The prevailing assumption dictated that only massive, closed networks had the capacity to deliver highly deterministic logic and flawless mathematical reasoning. Leanstral 1.5 offers a direct alternative. Built by Mistral AI, this model avoids conversational guessing entirely. It is explicitly engineered to write and verify formal mathematical proofs. The model drafts a proof and feeds it into a strict compiler. The compiler tests the logic, instantly returning an error log and new structural goals. The system automatically rewrites the code, cycling this verification loop rapidly until the math successfully compiles. Similar precision upgrades are happening across data classification. Google's TabFM applies zero-shot in-context learning directly to tabular data, reading complex tables accurately without needing dataset-specific training loops. Open-source systems are no longer guessing at the right answers. They are structurally proving them, making expensive cloud hallucinations a thing of the past. When you combine hyper-compressed architecture with deterministic offline logic, the application layer moves out of the terminal and directly into the physical world. The release of the LeRobot v0.6.0 toolkit connects these elements by embedding predictive world models directly into the control systems of physical robots. Running completely offline, the system's artificial intelligence can simulate and rehearse the physical outcomes of its actions in a latent digital space. It tests its movements internally before commanding the hardware to execute the task in reality. This grid maps the resulting deployment landscape of 2026. Whether utilizing a mobile edge laptop or a multi-GPU workstation, Developers can perfectly align their hardware with specialized local runtimes to independently execute stateful multi-agent graphs, formal math verification, and live robotic control. The era of paying rent for API access is ending. Artificial intelligence is no longer a centralized service to borrow. It is foundational infrastructure you can fully own.